Let's start with number 48. On 48, they say that S represents weekly sales of a product. What can be said of S prime and S double prime for each of the following statements? So for A, they tell us that the rate of change of sales is increasing. All right, rate of change of S. What's another word for rate of change of S? Derivative. It's first derivative, right? Rate of change, derivative. So if the derivative is increasing, what does that tell us about S double prime? That it's positive. Okay? Now for part B, sales are increasing at a slower rate. So the sales are increasing. If the sales are increasing, if S is increasing, what's that tell you about the sign of the derivative of S? That it's positive, okay? But now think about this. If the derivative is positive, let's see, how do I want to word this? If the sales are increasing, but at a slower rate, they're going up, but they're doing that, they're getting so that the S prime is going to have to be decreasing. If the rate is getting slower, the derivative is getting smaller, right? So the derivative is positive because S is increasing, but it's increasing at a slower rate, so the derivative is positive, but the derivative itself is not increasing. The derivative is decreasing, which means S double prime is negative. Y'all follow me on that? All right, let's look at C. The rate of change of sales is constant. All right, so the rate of change of sales is constant. That means, well, if you have a constant function, what's its derivative? Yeah. Now, if you notice here, I put C because I think they mean the rate of sales. I think, well, how'd they say it? The rate of change of sales is constant. So let me subtract what I said. It's not the sales that are constant. It's the rate of change of the sales that are constant. So C, some constant for rate of change, derivative. And then if the derivative is a constant, its derivative has to be 0. C makes sense? All right, D. Sales are steady. Now this is what I was almost thinking there on C. Sales are steady. I'm thinking they probably mean, right? That's what I would call sales are steady. So if the graph of S is a horizontal line, its derivative is 0, and the derivative of 0 is 0. E. Sales are declining. All right, so S is decreasing. Sales are declining. S is decreasing. So S prime is negative. All right. But the sales are declining at a slower rate. So the rate of change is negative, but it's slowing down. So the sales are doing this, right? But they're getting less negative. So the derivative is going to be negative, right? Tangent line, tangent line, tangent line. But what's the derivative doing? It's actually increasing, isn't it? Which means S double prime is positive. Notice that this question and this question are asking the same kind of thing. So you with me on those two? And the last one. Sales have bottomed out and have started to rise. Okay? So if the sales are rising, we know that S prime, the rate of change, is positive. But they don't give us any more description like they did in B and E to know whether or not, whether or not the sales are looking like that or looking like that. So we really can't judge S double prime, can we? We can guess, but we can't know for sure. So all I put on that one was that the derivative, the rate of change, is positive. Does that help for 48? Now do you see why business majors have to take calculus? They have to be able to study graphs and stuff like this and notice, rates, because rates matter, don't they? All right, it's not enough to know that just what your sales are. It's nice to know if they're increasing, decreasing, bottoming out, what's the curve look like, all kinds of things that I don't know about business. I just know I can help them with the graphs. I don't know. They have to draw the conclusions from them. All right, what else? 29. All right, come on. Windows 7. All right, 29. The directions tell us to find all relative extrema, use the second derivative test where applicable. So on 29 here, we have f of x equals x minus 5 quantity squared. If I'm going to use the second derivative test, there's a lot of things I've got to do before I can use the second derivative test. I've got to find the first derivative, and I've got to find the second derivative. I've got to find the first derivative because I have to find critical numbers, and because I have to have the first derivative before I can get the second derivative. I've got to have the second derivative because they want me to use the second derivative test. So I find the first derivative, and I could have squared that out, but I thought chain rule worked pretty well here. If f of x equals u squared, f prime of x will be 2u times the derivative of u. So 2 times x minus 5 times the derivative of x minus 5, which is 1. And then the derivative of that, I can use the constant multiple rule, so that'd be 2 times, well, whatever the derivative of x minus 5 is. And like we just said, the derivative of x minus 5 is 1. So that's my first derivative and my second derivative. Critical numbers occur when f prime of x equals 0 or f prime of x does not exist. F prime is a polynomial. It's gonna exist. Okay? Now, it can equal 0, though. So f prime of x equals 0 means that 2 times the quantity x minus 5 equals 0. So figure that out. 2 doesn't equal 0, but x minus 5 equals 0. You'd add 5 to both sides. X equals 5 is your only critical number. So you with me down to the critical number? All right, now the second derivative test. Remember how it works. You want your critical number, and the critical number has to be one where the derivative equals 0. Don't use one where the derivative does not exist. You might as well just back up to the first derivative test. Okay? We want to know what the sign of the second derivative is. All right? And then we'll reach a conclusion about relative extrema. And the only critical number is 5. The second derivative is a constant. It's 2. 2 is positive. So the second derivative is always positive. Now, that seems a little confusing at first, but think about what's going on. If the second derivative is positive, doesn't that mean our function's concave up? And since the derivative equals 0 when x equals 5, doesn't that mean if that's x equals 5, that's a horizontal tangent line? So whenever those two things happen together, you have concave up and a horizontal tangent line, you have a relative minimum. Yeah, because when you put 5 back into the function, you get 0. So I'll see if I can scoot this down. I don't know why it won't let me. You can do that so you can see it all. So all I did to end it up was to say that f of 5, which equals 0, is a relative minimum, or if you'd prefer to say 5, 0 is a relative minimum. I don't really care how you word it, as long as you let me know that the minimum value is 0, and it occurs when x equals 5. So, wait, did you say y-axis a while ago? Yeah, looks something like that. Yeah.
So, you find the critical numbers, and once you find the critical number, that is
Yeah. So this one, the only thing we skipped was we weren't able to plug 5 into the second derivative because the second derivative is constant. All right, what else? 15. All right, on 15, we're supposed to find the points of inflection and discuss the concavity. All right, on 15, when in doubt, start finding derivatives, right? So on 15 here, we have f of x equals x times the quantity x minus 4 quantity cubed. Tell you what, let me stop that for a minute. If we're going to talk about concavity, remember how concavity works. So instead of me showing you the process, let's do the thinking of it first. Okay? Concave up means f double prime is positive. Concave down means f double prime is negative. Right? The only way the concavity can change is by the second derivative changing from positive to negative. And it's not like the second derivative causes it. Remember, it all happens at once. Okay? Concave up, first derivative increasing, second derivative positive, all go together. Concave down, first derivative decreasing, second derivative negative, all go together. So, the only way the concavity can change, though, if the concavity changes, the sign of the second derivative has to change. Well, the only way that can happen, to change from positive to negative or negative to positive, is if the second derivative equals 0 or does not exist. So we got to find our possible points of inflection. Point of inflection is where the concavity changes. So the only way the concavity can change is if the second derivative equals 0 or does not exist. So we got a lot of work to do here to figure out where the second derivative equals 0 or does not exist. So I find the first derivative, which takes me a bit. It's a product rule with the chain rule inside of it. First function times the derivative of the second. So think of that as u cubed. So its derivative will be 3u squared times the derivative of u. So there's 3u squared times the derivative of u, plus the second function, u cubed, times the derivative of the first. Okay? Then we simplify, and I simplify it down to there. But when I take the derivative, and I could have taken the derivative like that and probably should have just done the constant multiple rule, said 4 times, and then taken the derivative of that. Well, I didn't think of that, I guess, when I worked this. So instead, I used the product rule, first function times the derivative of the second plus second function times the derivative of the first. Had to chain rule that derivative of the first one. Fortunately, even if I forgot, it would work out okay because the derivative of x minus 4 is 1. So sometimes you get lucky and you forget and it still works out. So then finally, work, and you get down to there. So take a minute to look at that. We okay down to the check mark? I'll put it back up in a minute if you just want to finish copying. Everything seem okay? Why won't it do that? Oh, thought I could trick it. All right, well, let's keep going with what I can show. All right, so our new magic sentence down here, a point of inflection can occur only when f double prime of x equals 0 or f double prime of x does not exist. F double prime is a polynomial. All right, it's not written out as a polynomial, it's factored, but it's a polynomial, so it exists. But I can set f double prime equal to 0, so I get 4 and 2 as possible points of inflection. All right, so our test for concavity. It's a lot like the first derivative test because we're concerned with the sign of something and then we reach a conclusion from it, but it uses the second derivative, okay? So make your interval go from negative infinity to your first possible point of inflection. Make your next interval go from that possible point of inflection to the next one. You keep going from one to the next till you run out. Then you go from the last one to infinity. Then the test number doesn't matter other than we just need something to help us decide the sign. The sign of the second derivative will not change on this interval. I know that it won't because it can't change signs without either going through 0 or not existing. And the only place only two places either of those things happen are at 2 and 4. So from negative infinity to 2, the second derivative cannot change sign. So let's figure out what its sign is. So if you take 0 and you put it in here into the second derivative, you'll get 12 times a negative times a negative. Well, that's positive. And a positive second derivative means the first derivative is increasing, which means concave upward. Then we do the same idea on the next interval. I chose 3 this time because it's between 2 and 4. So the first parenthesis is a negative, the second parenthesis is a positive. So 12 times a negative times a positive is negative. Second derivative negative means first derivative decreasing, means concave downward. Then for the last one, I chose 10. If I put a 10 there and a 10 there, I get 12 times positive times positive. So the second derivative is positive. First derivative is increasing. F is concave upward. So we do have concavity changes when x equals 2 and when x equals 4. So we have points of inflection when x equals 2 and when x equals 4. How did I find the y coordinates for those points of inflection? Plug them in to the original. So the little roller thing on the mouse works, even though the grabbing it and moving it doesn't. Okay? Does that take care of 15? That's where the graph crosses its tangent line. Well, right about there, this graph changes from being concave up to concave down. While it's concave up, the graph is always above. Do what? To have a point, yeah. Now here's the thing. We could have concavity change at an asymptote, and some books allow you to call that a point of inflection, and some books say don't call it a point of inflection because there's not a point because it's an asymptote. Just say that the concavity changes. So you'll see that either way. Am I answering your question at all? Okay. All right. One more. If you got it. Okay. No more questions means it's time for your assignment. So your assignment starts on page 195 again. Page 195, do 17 through 23. I meant to put odd on that. 33 through 39 odd. And then 49 through 57, do all of those.